So welcome. So my name is Clement Escoffier. I'm working at Red Hat in the Vert.x team. And before talking about Vert.x and OpenShift, you need to know something about me. I'm a former academic. I'm a former teacher in university. And you may see in my slides and in my talks that I will quote a couple of very old papers from the 60s, 70s, 80s. So that's normal. That's usual with me, so don't worry. I still believe that we didn't invented anything since the 90s. We just rebrand things. And today I'm going to talk about microservices with OpenShift and Vert.x, but reactive microservices and Polyglot microservices. So if you don't know OpenShift, it's actually a cloud platform. It's a layer on top of Kubernetes, and it will let you manage, deploy, coordinate your applications and deploy running inside containers. We will see OpenShift a bit inside this presentation, but I will focus more on Vert.x and its polyglot aspect. So let's summarize Vert.x in 10 slides, and actually I can summarize Vert.x in a single sentence. Very fuzzy, very high level, but that one works. I come up with that one. So Vert.x is a toolkit to build distributed and reactive systems on top of the JVM using an asynchronous non-blocking development model. Yeah, I tried to put a lot of buzzwords in a single sentence. That's not that easy, actually, and to still have some sense at the end, but now we can actually try to explain all those buzzwords. The first thing to understand about Vert.x is that Vert.x is not a framework. Vert.x is not a container in the sense IOC, dependency injection, and so on. Vert.x is not an app server. Vert.x is just a library. It's just a toolkit. And that's really important because this particularity makes Vert.x really, will give you a lot of freedom. You will be able to do whatever you want with Vert.x. You can run a Vert.x application by just doing a main, so a public static void main, and that's all. That will be a Vert.x app. You can embed Vert.x. You can embed Vert.x in a Spring application. You can embed Vert.x in a Play applications. You can embed Vert.x in a Java EE application if you want. That works too, because one, it's just a library. So Vert.x is packaged as a plain boring jar. And actually, when you build a Vert.x application, generally, you just take those jars and put them in your class paths. That's all. And all the Vert.x components that we provide are actually just plain boring jars. There's nothing complicated. Everything is relatively simple. So you can pick the format you want to package that. So for example, these slides here are actually running on top of Vert.x. So it's a HTTP server that serves a lot of resources. Imagine that's HTML5, so the number of pictures, CSS, and so on that I had to deal with that. But this is a jar. Then I took a couple of other dependencies, Vert.x Web, which is a component to build modern web app. A modern web app, it's all about REST, bidirectional communication with the browser, templating, and stuff like that. I have a cluster manager, which is Hazelcast for today. I'm taking some risk because Hazelcast and OpenShift, we have some issues, so let's hope that it's going to work. And service discovery, because it's a talk about microservices, so we need somehow to do service discovery. Then I have a couple of dependencies, Vert.x Core, of course, and then Jackson and Netty. That's all. So actually, if you just take that, it's really, really small. We are really far off the 60 megabytes we need for some other frameworks and stuff like that. From this, I built a file jars, and these file jars are around 15 megabytes. It's mostly pictures, but yes. And these file jars, I've write a Docker file, and I send that to OpenShift. And OpenShift is going to build this and create a container and deploy it inside a pod. So it's this here. So that's the OpenShift dashboard. And what we have here is my slides application here. And I have one pod running. A pod, what is a pod? Theoretically, it can be a set of containers. In practice, it's generally just one container. So it's just a Docker container that is running, instantiated. And you see that we can scale, we can do some stuff. We will see that later. That's all. And then I get everything running. So that's actually very simple to deploy containers on OpenShift. You don't need to think a lot. You just give what you want, give a Docker file, and OpenShift build it for you. So you don't have to do that. Vert.x is made to build distributed systems. And actually, we had in the keynotes and in the talk I've attended before, a lot of explanation about what are distributed systems. But actually, I think the best definition of distributed system is this one. This one comes from the 80s, from Leslie Lamport. It can be summarized that, well, distributed system is something that fails. You can be as smart as you want, you can be a genius, it's going to fail, that's all. That's the constraint of distributed systems. So you need to be prepared to fail. You need to be prepared to handle those failures. There is nothing you can do, they will be there. So then you can choose between two alternatives. You can use a framework that will try to hide this complexity. Well, the only issue is that this complexity is never completely hidden, and you may have to debug something at 2 a.m. in the morning in a production system because, well, something wrong happened. Or you can use a toolkit that won't hide it. No, it won't hide it. It will tell you how you can handle it. It will embrace the complexity, because anyway, it is going to be complicated. We won't build any kind of distributed system. We are going to build reactive distributed system. That means that all our components in our distributed systems are going to be responsive. Well, they will be fast. Vert.x is actually very fast. They will answer to a lot of different requests at the same time. So we handle a lot of concurrency. For Vert.x, 10,000 connections at the same time, it's nothing. It's going to be elastic, and actually that's something that we will see in this talk. Scaling will be very, very simple. I will click on a button in OpenShift, and that's all. I've scaled up. And I can scale down by pushing the other button. It's going to be resilient. Well, as I said, it's a distributed system, so anyway it's going to fail. So the system we are going to build is going to have a lot of failure handling and code to handle that. And it's going to be completely asynchronous. Vert.x, the application of Vert.x run on the top of the JVM. That doesn't mean that they have to be developed in Java. That means that they can be developed in Java, as we have here. So we just create an HTTP server and say, hello, Java. It can be also developed in Groovy, that's this example here, or in JavaScript, or in Ruby, or in Ceylon, and before the end of this year, in Scala. Scala is going to be a first-class language of Vert.x during the next release. What does support mean? That's a large difference with other frameworks. When we say support, when Vert.x supports a language, that doesn't mean that you use the Java API from this other language. That doesn't mean that you use the Java API from Scala, for example. Because when you do that, well, Java and Scala are very different, and the idioms, the construct of the language are different. So it's always weird to use the Java API because, well, something not natural here. So what we do in Vert.x is that we generate all our API to all those languages using the idioms of the language. So for example, let's take JSON objects. In Java, well, we have a JSON object class because it's Java, so there is nothing about JSON in Java by default. So we have provided a JSON object class. In Groovy, we will use maps, because Groovy maps are really nice for JSON. So we have key and value. While in JavaScript, JSON, well, it's just an object, and so on and so on and so on. So every time we support a new language, we actually generate all our API for this language with the idioms and the construct of this language. So, okay, let's switch a little bit to microservices. Jonas said it this morning. I don't like the name either. I generally call that federated services. But the core ideas behind microservices is just refurbish distributed systems. We tried and failed to build complex distributed systems in the 60s, and in 2016 we will succeed? Well, that's not that simple, and we are going to see that. There is no consensus on what microservices are, but I like this definition, which is high level enough and fuzzy enough and give not much detail, so almost everyone find something on which they agree inside this definition. What I like in this definition is architectural style. Martin Fowler says that microservices is an architectural style. So an architectural style, it's a set of entities and connectors and a set of constraints that will define how those entities and connectors are plugged together and interact. Set of entities, that really join what was presented this morning. A set of entities is at least two entities. So you can't have a microservice architecture if you have only one entity, because, well, it's not an architectural style. You need at least two things to build an architectural style. Then there is many things that we are going to see. This part here is a bare minimum of centralized management. It's where I disagree a bit with this definition. So when we build a microservice system, we actually are going to build a federation of services. And each service is going to run in its own process, and actually in OpenShift in its own container. So it's really isolated. It can be across different data centers and so on. They're going to interact because the business value of your system comes from the interaction between those services. One service is alone, we don't care. It's just useless. It's the federation that creates the value. About the interactions between the services, there is no silver bullet. You will have to pick the ones that make sense for you. You can use HTTP. It's actually a lot of people are using HTTP. I won't use the term REST because we can have a debate for months about the restfulness of all the HTTP API we found nowadays. So it's just going to be some HTTP-based interaction. It can use messaging, so the coupling is a little bit more loose. It can use streams, or it can use RPC. That's weird, right? Everything we say about microservices is, oh no, RPC is a past. Well, RPC exists in the 70s, and it's probably going to exist in the next 20 years. So sometimes you can use RPC, and it's not bad. It's better when it's asynchronous for many good reasons, but it's still RPC. What makes microservices really, really successful today is that it meets the requirements of modern software development in the sense that we need more agility. We need to be able to make mistakes and to repair those mistakes. So how does that work? Let's imagine that you have read a couple of blog posts about a new cool stack, and you absolutely want to try it, and you implement one of your microservices using this stack. It works. It uses, maybe HTTP to interact with other microservices, so it's fine. But you realize that in production is not that great. It lacks a bit of maturity, and the integration with the rest of your stack is not that good. So, well, you actually made a mistake. And it happens a lot. What is great with microservices is that, well, you can re-implement it quickly. Because normally you should just do one thing. So it should not take too much time to re-implement it. And as soon as you re-implement the same interface, not Java interface, but the same way to interact, to invoke this service, well, you can replace it. You can actually replace it dynamically. So all those services are going to be developed individually. Developed, tested, deploy, update, release, dropped, put under updates, and so on. That's actually very interesting because what is going to happen is that we have a dynamic system where everything is going to move. And how it works, how it can work, is that actually every node is going to be autonomic. I won't use the term autonomous, I prefer autonomic. There is slightly some difference between them. So everything, all those nodes need to be aware of its surrounding and react to that. But, well, and it's where I mostly disagree with Martin Fowler's definition, is there is no free lunch today. There is absolutely no free lunch. You do your microservice with the stack you want, with, well, let's say Vert.x, for example. You need to think about a lot of things beforehand. You need to think how you are going to discover those other services that you are going to use and how you are going to announce yourself to be used. You need to think about reliability because everything is going to move, everything can fail, so you need to think about that. How you are going to deploy and to deliver your service. This is something you need to think too, and how you are going to manage the dynamic availability of all the services you are going to use. So you need to think about all of this. And that's just the first circle. Then you need to think about distributed tracing, logging, API management, or it's going to scale, or do you do load balancing if you want to have A/B deployment, canary build, also security, authentication, fault tolerance, monitoring, and so on, and so on, and so on. So from something that looks simple on the paper, I don't know if you have already deployed all this in it together, it's far from being simple. It's really, really far from being simple. So what Vert.x brings there? Well, Vert.x will let you build those reactive microservices with first failures are going to be a first-class citizen. You will have to handle them. It's going to be able to reply to a lot of connections, and updates and so on is going to be fast, so that's good. Elasticity is given. We will see. We will just start a new node, and that's all. Round robin is built in. And it's going to use an asynchronous message passing model. So what does that mean? That means that everything is asynchronous. So instead of waiting for a return, you will invoke an operation, pass some parameters, and pass a callback. And this callback will be called when the operation has been completed. That's what we have here. We can use callbacks like that. So here I have an HTTP server, and every time I have a request, I will first execute the operation A, and then execute the operation B when I have the response from A. So the callback of A is there, and then we have B, and the callback is there. And when I have done, I can just compute the response of my request. Well, you can see, using callbacks, when it starts to be a bit more complicated, may become really, really hard. So that's why we don't provide only callbacks. You can use features. So that's not Java features, that's not Scala features, that's just Vert.x features. And a feature is what? A feature is like a promise, actually. Promise, the term promise were coined in 1976, while features were coined in 1977. So yes, there is nothing new again. Promise and features, that's from the 70s. So with features, your operation is going to return a features, and this feature is going to be completed when the operation succeed or failed. So it might be marked as a failure or marked as a success. And then when you have features, you have operations, so high-level operators to compose them, like here I do an whole, which means that I'm going to wait until all of them have completed, or the first one has failed, to execute this callback here and just reply. Well, if you're in the Java world, it seems that we have a lot of Scala users around, but maybe you did some Java at some point. In Java, we have something called completable features. And actually a nice class. It's really efficient. The implementation is really weird because it's all based on a class that is named unsafe, so it's just memory management. But so it's really fast, but it works quite well. And what you can do in Vert.x is, well, returning completable features. And then you don't have to learn a new API. You will just use the completable features operators like Olaf, then run, accept, and so on, and so on, and so on. So how does that work? Actually, we implement in Vert.x completable features, well, in a separate project, using the same API, and we can just use that. Or you can go really on the hype and use functional reactive programming, in the sense that reactive programming is a subset of functional programming where you handle streams, and use Rx Java. This code is still valid Rx code, Vert.x code. You can use that and get some observable from A and B, and then zip, so meaning that you take the first element of both streams, and then you join them with this operation here. And just once this is done, I subscribe. So when it's done, I just write my response. So in Vert.x, you pick your own language. You pick how you want to start it. A main, inside Spring, inside Play, inside Java EE, whatever. You also pick your own development model. You like callbacks? Why not? All Vert.x core is all based on callbacks. From my experience, you should not use callbacks every time, but well, it's up to you. What does Vert.x will provide you? So Vert.x, it's a toolkit, and we provide some basic block. We don't provide an all-in-one solution. We'll provide TCP, UDP, HTTP 1 and 2 server and clients. Obviously WebSockets too. A non-blocking DNS client, an event bus for messaging, a distributed data structures. So again, it's not for all the nodes to share states. That's not the goal of data structures. Data structures are there when you have more than one instance of your service and you need to coordinate this. Built-in load balancing, built-in failover, service discovery, failure management, circuit breaker, shell, metrics, deployment support, and so on and so on and so on. So it's really a toolkit, and from this you will put the element you want, and you can build your own framework, your own application with that. It's really a lot of freedom. But it's time to see some code, and we will start with some REST, obviously. So that's the Vert.x hello world, and well, that's very simple. So generally, when you start Vert.x, you will start to do this code. So you create an HTTP server here, Vert.x.http, create HTTP server. Then you have a request handler, and this request handler, so this callback here, is going to be called every time there is a new request. That's simple. Yeah, so in this presentation, I will use a callback style, so you don't have to know all the other API. I will mostly use Java. There is this part here that is actually interesting, is starting an HTTP server takes some time. And as I said, Vert.x is fully asynchronous. So you don't want to block here. So what you do is you say, well, tell me when you're done. So this callback here is going to do that. This parameter here is an async result. An async result is a structure that will contain the result of my asynchronous operation. So it can be a success. Woohoo, everything fine. So you can get the result. Here it's my HTTP server, but it's useless. Or it can fail. There is many reasons why starting an HTTP server can fail, like, well, you forget to stop the previous one, so you have a conflict on the port, or well, we all did that, right? Forgetting to stop the first application and starting everything on port 8080 or 9000 and so on. So here, at least, you get the calls, and you can see that. But let's have a look at this code. So it's mostly the same code. So as you see here, I have a main class. Well, it will just be a main class. I don't need anything else. So it's going to be, well, packaged in a file jar, put on OpenShift, actually it's already done. And I create my instance of Vert.x here. I create my HTTP server. I do my request handler here, so it's a bit more complicated because I just want to display the dates and the thread. It's always interesting to display threads. And that's all. So this is actually running right now, hopefully. And it's, which one it is? It's this one, so I have one pod and so on. So if I go there, oops, and I invoke it, it doesn't work because the DNS is yes. Haha, I knew it will happen. And distributed system, I told you. There is a trick to do that. Generally, it makes things a bit better. Let's see. No. No, still no. Not just the DNS. Well, let's scale down and scale up then. So what I'm doing here, I'm just restarting it and to see if the DNS is back again. It's always tricky to do this presentation on hotel Wi-Fi because lots of things can go wrong. And typically, this is the first thing that can go wrong. Okay. So what you can do with OpenShift, so you can do that. You can have the logs. You can actually have the terminal inside your Docker container, so you can really check what's going on and stuff like that. So obviously the pod has been killed, and now I will just restart it. Which one it is? Up here. I will start my pod. There we go. If I go there, so that's my pod, and I've seen the logs, so normally it should be better now. Ah, that's a bit better. Yes. So it seems to work. Woohoo! Sorry about that. Well, distributed system, it's fail. we know that. So what it's doing here is that my slides are actually calling the code you have seen, and I had to restart. And so it's just writing a host in, the date. So as you can see in distributed systems, the notion of time is kind of weird because it's absolutely not that time. But well, it's because I put my laptop asleep and so on. And this is a thread. That's interesting because, well, it's mentioned event loop. I didn't not mention event loop yet. So what an event loop is, this is a simplification, but actually it's very, very simple. An event loop is just a thread. And when you build an event loop, you will have a queue somewhere, a queue of events where you have event providers that just will enqueue those events inside this queue. And then this thread will get the next one, find an interested handlers, and dispatch it. Will it dispatch to all the interesting? The first one, it's implementation detail. But that's the basic concept of it. So the advantage of having an event loop is, well, there is a single thread. So you don't need to think about concurrency anymore. In the sense that your code will never be executed by two different threads at the same time. So no synchronize, no volatile, no lock, and so on. So no, well, the pleasure to debug a deadlock at 2 EM, well, that's dead. You don't have to do that anymore. The only issue with event loop is there is one golden rule. If one of the handlers here is a bad boy and decide to block, decide to say, well, I don't want to release the thread, I want to keep it. What is going to happen? So the thread is stuck here in one of those handlers. The other event provider will enqueue stuff until, well, you reach out of memory. So there is a golden rule with all event loop system never ever block the event loop. So in Vert.x, we actually have checkers to do that. So we check that your code is not blocking the event loop. You can configure that, of course, but yes. So we check that you don't break these rules. If you look at the title, I say event loops, because Vert.x is not going to use one event loop. It will use as many event loops as you have CPU cores. Why? Because, well, that way you can easily have an application that will use all the cores of your CPUs. We don't break this idea that we will always be addressed by the same thread. So once an object is executed by one event loops, we will keep executing this one using these event loops. But we will have more than one event loop. So that makes things really easy to scale. Okay, so we have seen an HTTP server, so let's now do the other side. When we have microservices, we also need to consume the service. And Vert.x comes with an HTTP client for that. So an HTTP client is just configured like this. You pass host and port, and then you do a get on slash. You have this callback to get the response, and if you're interested by the body, you just do that, register a body handler. The only issue is that when you do microservice, you don't know this. You don't know the post and the host. It's probably depend on your environment. It probably depends on a lot of things. And you don't want to write that down inside your code. You want to externalize that, or you want to use service discovery. Service discovery, again, it's very hard. We start looking at, well, the first roots of service discovery comes from the 80s. In a service discovery system, we have providers, and providers will announce themselves. They will publish themselves inside a registry or something. And, well, they can also withdraw themselves too. So say, well, I'm done, I'm leaving, so I'm not, don't call me anymore. On the other side, on the consumer side, well, the consumer will look inside this service registry or service discovery mechanism to find the services that are available, follow their change, maybe try to track them, and so on. So you don't need to hack or to know the host and port anymore because, well, if the provider has been registered correctly, the consumer can just look inside and say, oh, it's this one. How it will look it? Well, there is filters, there is many things to do that. An interesting part here is that, well, even if Vert.x has the own service discovery, you probably have your own too. You probably use Consul or DNS or Kubernetes or Zookeeper or, well, there is many of them. So what we do is actually we have a concept of bridge that will import and export our service records that we store here to those one, and we will import the records from here inside this one. And actually, when you use Kubernetes on OpenShift, we don't have this part anymore. Why? Because when you deploy a container in Kubernetes or in OpenShift, you have to say, well, expose this port. If you don't say expose this port, if you don't expose this service, well, Kubernetes will say, no way, we won't call you. So as you have to declare that in a manifest, well, Kubernetes is aware of this, and we are just consuming that and say, OK, we know who you are, and that's all. So you don't need to explicitly register yourself. Kubernetes is doing that for you. So if I do that, then getting my HTTP client to call my service is much simpler than before. You don't have to create the HTTP client. You just, well, if you know that it's an HTTP endpoint, you just do HTTP endpoint, get client, you pass the service discovery, you pass the filters. So either you pass a function, or a predicate, or you write a JSON object and it just match with the service property. And then you get the result. Well, it may fail because the service may not be there. Or it may be successful, and then you can just use it. So you don't, the only thing you need is, well, a name or whatever you use to identify your service. It can be a set of entries too, of course. And if I do that, this will be this code here. So it's what I do. So same thing, it's a main. I create my Vert.x, I create my service discovery. Then I register my Kubernetes service importer. That's all. That's just to limit the visibility to say, well, just import the services that are in the same project as I am. So a project in Vert.x, in OpenShift is what we have here. So all those elements. Oops, here. And oops, I was on my code. And that's all. Then I create an HTTP server because I'm going to call that. I get my clients on a request. I look for the client. Then, well, if I don't have anything, then I failed. Or I just call it and prepend hello to the response. That's all. And this is probably going to fail too. Yes, for the same reason. So I will restart that one. Where is the client? It's that one. So up, scale down. Scale up. So what it's doing right now is just doing the two things at the same time. So it's what the two pods we have here. I'm pretty sure I didn't start it 16 hours ago, so the timing is kind of messed up. To install, so this is my development environment of OpenShift, so I use something called Minishift, so you don't have to install anything, you just go to Minishift, github.com/Minishift, and it's a script that installs everything, and you get that working in a couple of seconds. Did it restart it? Yeah? Yes, no? Let's have a look where it is. So it's my HTTP client, here it is. Yes, so now it should work. Yes! Yeah, the DNS is kind of weird. Never use DNS for service discovery. It's my recommendation. It's kind of weird because of caching and stuff like that. So what we have here is that was my first service, A, that we have developed, and that's what we added in B, the one we just deployed and restart. So right now I have my browser that do an AJAX request to B, that call A, and compute the response out of that. So we start having a chain, so we start having a kind of a serious distributed system, even if it's just 3 elements. But, well, everything I said here is valid for TCP, UDP, and so on, but maybe you want to use another interaction style, and Vert.x will provide you messaging. Vert.x has an event bus, which is clustered, and so it will let any nodes, any components from this cluster to communicate using messages. So all those components will be able to communicate regardless, well, their implementation language, Groovy, Scala, and so on. Their location too can be anywhere on the cluster. And what is actually very interesting is that they can run on top of Vert.x, or they can be just external, something else, something not Java, something even not on the JVM, like .NET, Go, Rust, Python. Because, well, this language exists. And you probably have application using this inside your system. and maybe you want to interact with them. So this application will be able to interoperate with Vert.x applications using the event bus. It can also be C or C++, by the way. The event bus is structured around two concepts: addresses. Addresses are just opaque string. We don't have hierarchy. We don't have topics and stuff like that. So it's really pure opaque strings. And we have handlers. And we already have explained what handlers are. So it's functions that will get the message and will just process the message. So we have three types of delivery. I don't like this name, point-to-point, because actually what you do is that you get the event bus, you send to this address a message. Here I use a string, but it can be almost any object as soon as you can JSONify it. We use a lot JSON in Vert.x. And on the other side, you register a consumer on the same address, and here is my handler. Or here is useless because I don't do anything. Obviously, as we have point-to-point, we have publish subscribe. Okay, that's very simple. So here, instead of send, I just use publish. That's all. And we have something kind of interesting. It's request response, sorry. So you send a message to an address, and you expect a reply. That's kind of cool. Then the consumer gets the message and can reply to you directly. And then you can reply and reply and reply. So let's explain why we have that and how we can use that. Let's imagine that the sender is sending something, a message. Inside the payload is written actions equal hello, and program equals hosting. Consumer receives that and reply with hello hosting. That's RPC. That's actually an RPC call. You call a method, which I call action here, but that's just purely RPC, all based on messages. So see, you can do cool things with RPC. RPC doesn't mean that it has to look like Corba, even if I'm the last fan of Corba, actually, but well. So when we build the event bus, as I said, anything can interact with that. So it can be a C, C++ application, and so on. What I will show here is that we will have a node application and my own browser. This browser is going to receive messages from the event bus, my browser. It's definitely not running on Vert.x. This is Chrome, and they don't use Vert.x. So what I will do here is that, here, I will start a publisher, here, this one. So I already deployed it. So this publisher will join the cluster and will start sending every 5 seconds some messages to the event bus. And, well, let's see if my browser receives them. Oops. Here. Yes, no? So that's a cluster, so it starts to do something. Yes. There we go. So what we have here is just hello from Java to say, well, it's a Java publisher, and it's just a counter, and every 5 seconds it gets something. So, well, but here it's a Vert.x app. I could have used any language, but here I use Java. What we can do too is to start, on the first one, a node application that will mostly do the same thing. So if we look at the node code, I don't know if you are familiar with node, I'm not, but so we provide an NPM here. So Vert.x provide it. It's an NPM that we deliver with with our releases, and with this event bus client, so you can create a new event bus with some location here, and from that, once it's open, you can just use the event bus API. So here, every 5 seconds, I'm publishing some messages on the event bus. It's a node system, huh? So it's really a node. You can see that there is a package.json and so on. And if I go back to my slides, this slide here, now we have, well, that's your French lesson of the day. Java say hello, while Node say bonjour. That's all. So you can imagine almost integrating anything like that. Everything will be asynchronous, everything will be message-based. So it's not necessarily need to be a Java application. You can actually use anything. How does that work? Actually, we have bridges. And those bridges will just listen for a set of addresses on the event bus, and also forward using their own mechanism. So in this demo, I'm using a bridge that is a SockJS bridge. So SockJS is an NPM library too. That is more than 6 months old, so for NPM it's like forever, but well, it still works, so that's surprising. And how it works is that, for example, my Java publisher is sending my events, the SockJS bridge is receiving that, and forward you using a SockJS communication to my browser. So SockJS communication is actually, here it's going to use WebSockets. So SockJS will just negotiate how it works. So if you are using Chrome or recent browser, it's going to use WebSocket. If WebSockets are not supported, it's going to switch to SSC and so on and so on. If you're really using Internet Explorer 6, it's going to use iframe, but I don't recommend to use Internet Explorer 6. But well, if you do, it will still work. Node is going to do the same thing using the same bridge, and well, Node supports perfectly well WebSockets, so it's going to use WebSockets too. So what we provide in terms of bridge, we provide SockJS, we also provide TCP, obviously, because a lot of language support TCP. And then we have also Stomp and MQP when we just wrap other message system, and we have Camel. Camel is kind of interesting because it's not because you have a reactive system that the rest of your system need to be impacted. You may have a very old application, let's say legacy. Legacy is kind of a bad word today, but well, imagine that you have legacy application and you still want to interact with them. How do we do that? So maybe they are even developed in COBOL or whatever weird language that we're using at that time. So Camel is a mediation framework that will let you do that. And using the Camel bridge, it's going to be an asynchronous integration with your legacy system. So you will never block. You will send an event on the event bus, the Camel bridge will receive it, it will go inside something called a camel route that will do the negotiation, the mediation, and so on, calling your old system, and then coming back, and using the reply mechanism of the event bus, you will get the reply. Non-blocking asynchronous integration of your legacy system. Simple. There is absolutely nothing new inside, but it works pretty well. If you have clients, if you are using Go, C#, and so on, we provide clients, which means, an API like we have seen for Node, which is directly developed in the language. So we provide Go, C#, C, Python, Swift, and a couple of other ones. I'm always forgetting some. Okay, but well, in microservices, remember we had this inner circle, so we saw a bit discovery and availability, but we need to have some reliability pattern. And yes, it's absolutely impossible to be bulletproof. It's a distributed system, so you have to be prepared to fail. So the first thing we will do is actually having timeout. Well, timeouts are kind of a simple way to detect failures. That's not really true. I will come to that. But all the interaction and all the synchronous operation you will do with Vert.x have a way or another way to pass timeout. Why timeout are a bad way to detect failure? Because, well, and we know that since 1985. I have A and B, and let's say A get a timeout. What does that mean? That means that something bad happened between A and B during the execution of B or on the way back between B and A. So if it failed or something bad happened between B and A, the operation has been completed, but just the message was lost. So that doesn't mean, a timeout doesn't mean that the operation has failed. That means that something bad happened on the way in, inside the operation, or on the way out, well, on the way back. So you need to think about that. And if you start thinking that timeout that we use every day is actually not a really good way to detect a failure, then that will make your life way more interesting or complicated, depending on your point of view. So you need to think about idempotence and stuff like that. So let's have a look to that. Oh, this is probably going to fail for the same reason. Oh no, maybe not. No, sorry, that's not the right one. That's this one. I did a very bad consumer here. And this consumer is actually, well, failing 50% of the time, almost 50%. I'm using a random. And if it fails, then it doesn't reply. And if it doesn't reply, the sender is going to get a timeout. I think I have configured 3 seconds. So if I do that, well, it decided to fail. That's a very bad one. And maybe this time it's going to work. No, okay. Really unlucky. Oh, yeah, now it works. 3 times, and now a failure again. So with this, you can easily, well, detect not failures, but detect things that, well, you are tired to wait, and you want to continue your execution and consider that as a failure. Another way to handle failure is circuit breakers. So circuit breaker became really, really popular since a couple of years, while circuit breakers come from the 60s too. Yeah, nothing new, right? It was actually used in operating systems. It's kind of cool. And there is probably still a lot of circuit breaker inside our own operating system today, so my Mac or Windows or Linux and stuff like that. So a circuit breaker is very simple. It's a 3-state automata. We start in the closed state. We monitor an interaction. And every time that this interaction fails, then we increment a counter. And when we reach a threshold, we go to the open state. In the open state, we won't call the operation anymore. We will immediately call a fallback. Because, well, we know it has failed. But what makes things cool is this loop here. Periodically, it will attempt to go to this, it will go to the alpha open state, and it will let the next call pass. And according to the response, to the result to this interaction, it will decide to go back to the open state if it failed, or to go back to the closed state. So why it's interesting? It's interesting because, well, it provides a kind of auto-recovery mechanism. So it failed. Okay, I'll stop calling that, but periodically we'll try to see if it's back. So that's the first thing. But it's also a question of respect. So, well, it's that weird, because services need to respect each other. If you have services that start to be slow, that start to be in bad shape, it's completely useless to continue to sending him requests. Actually, it's even worse, because you will make his state even more tricky, and, well, it won't recover like that. With a circuit breaker, you will stop calling it. So it gives them some time to, well, recover, take some fresh air, and be back online. So in Vert.x, we provide our own circuit breaker. You can also use Histrix if you want. The issue with Histrix is that you need to be careful that you need to be called in the same thread as a caller, so because it's not on the event loop. While the one we provide is actually one made for asynchronous operation. 2 will enforce the Vert.x execution model. So I execute some operation with a fallback. So for example, an HTTP call. And well, if everything's fine, I say, okay, I'm done, so I just complete a feature that was given here. And if anything bad happens, I would just say, well, fail. And if it fails, then I just do sorry. That's all. So if I call that, yes. So here it's the same example, so everything is fine. Everything is working perfectly, but now, if I stop the server, this one here, tack, scale down. Yeah, OpenShift tell me, well, are you really sure you want to scale to 0 pods? Because that's kind of weird, like, well, I'm really removing something, so that's why I have this dialogue. So now that it stopped, so the first thing is that, well, I will reach some timeout, because, well, the server is not there. And see, my circuit breaker is in the closed state. And now, I reach my number of failures, so that was 3. I'm in the open state, and so it's immediate. And at some point, I go back to the half open state, and it retry, get again a timeout, and now I'm back to the open state. Oh, sorry, half open. So it's immediate. So I don't try to call A anymore. And as soon as A restarts, back. It should work again. So I have a recovery mechanism, very simple. Okay, well, that was for resilience, but we need to speak also about scalability, because imagine that you have a really, really great application, and I believe you have, but failing because you are not prepared to handle the load, this is kind of sad. Because if you did this great application, you really want to have something that works. So we never know, be prepared to be famous. There is a couple of elasticity patterns. So first, we have this vertical scalability using several event loops. That's one. And we also have horizontal elasticity in the sense that, well, we will just start new node. So how does that work? Every time you send a message, Vert.x is implementing a round robin. And the first thing is that it will call A, B, C, A, B, C. So if you have a lot of messages arriving, just start a new node. And to start a new node, that's very simple. So for example, here, I have one node that handles my request. Every time I call invoke, it's send an event and reply to it. But if I'm here, so which one is that? No, I don't want to do lookup. I don't even know what it is. Here, if I just click on this, and the cool thing is that with the latest Kubernetes, you can have auto-scaling ability, so it will monitor your usage, and if you reach a level of usage, it will just automatically scale to the number of pods you said. So now I have 2, and it will, we're here. So now, as soon as the second one is ready, we should start C. So it's a non-strict round robin, so that's normal that sometimes it just doesn't align it. And that's all. And you have really a lot of messages happening, you just start more pods, and that's all. And when it's done, just stop them. That's very simple. Well, that was for the event bus, but for HTTP, how does that work? Actually, Kubernetes is doing that for you. Kubernetes, every time it gets HTTP request, will implement a round robin on the set of pods that you have started. Or, if you have really a large REST API or something like that, you can forward those requests to the event bus and have the scalability and scale all the parts individually. So what I've presented here is that Vert.x will give you the freedom to implement your own application using the pattern you want, the language you want, and it's perfectly suited for microservices. What OpenShift brings you is that it will bring you all the deployment facilities you need based on container, which are kind of appealing, but it will also provide a couple of things like monitoring, built-in monitoring. Here it will be very simple, but we have also a dashboard and stuff like that. Soon we will have distributed tracing. We also have configuration. We have a secret management and so on and so on. So OpenShift is going to provide almost everything on this outer circle, while Vert.x will handle the inner circle on your application. So the combination makes it very, very cool and very easy to develop microservices. Well, if you want to start, then OpenShift.org to start downloading OpenShift. I recommend you to use Minishift or CDK. Vert.x, Vert.x.io. On this blog post here, it's a series where we start to implement, it's to implement a REST application using Vert.x with JDBC and so on, so Mongo too, so it will tell you everything you need to know. This hands-on lab here is a very long hands-on lab. It's 70 pages. It's about reactive microservices. So everything I have explained, but really more in depth. And we build in this lab a micro trading application, so a fake trading application. I just want to mention this. Microservices are great, but we need to think about security, and we're actually in a research project where we are using a new generation of CPUs made by Intel to ensure the security and the privacy of your code and of your data. And while the last thing, there is the JAX Innovation Awards. If you like us, just vote for us. Thank you very much. If you have any question, well, I will be around. I don't think we have no time, so I will be around. If you want to see other demo like how to load and stuff like that, well, just ask. I have many things to show you. Thank you.